Hello everyone, this is going to be my first video on the channel. The topic we are going to start with is work, energy and power. I decided to start with the topic because around this time I believe almost everyone is doing the same topic in schools and universities these days. So I thought let's start with this topic. However, it is required that you have an understanding of forces and kinematics before you start watching this video. So make sure you do understand how forces work, what is a net force, and what are the different types of forces which you study in Unit 2, basically, which is Newton's laws of motion. Okay, so without any delay, let's start with the discussion. Now, the topic is work, energy, and power. So let's start with work. The very first question is, what is work? What is your understanding of work? Now, this video is going to be interactive, so I will be asking you questions. So every time I ask you a question, you can stop the video and then take a minute to think about what is your own understanding of work. And then once you have an idea or your own definition, you can again start the video and see if your understanding and my answer matches with you. So this is how I would suggest to watch all the videos which I will be uploading on the channel. Every time I ask a question, pause, whether it is a numerical or a theoretical conceptual question, pause the video, take a minute, solve it, understand it, explain it yourself, and then start the video, continue with the video. Okay, so what is work? What is your understanding of work? You can pause the video and think about it and then come back. Now, what is work is it is a method of transfer of energy. When suppose there is a box and the box is at rest. At this point, it has no extra energy. It is just simply resting on the table or on the ground. Now, push the box, that is, you apply a force on the box. What is going to happen? If the box is movable, then the box is going to move from point A to point B. In doing so, it covers a displacement. Let's say this displacement is d. But before you applied any force on the box, it had no extra energy to go from point A to point B. In fact, it had no energy at all to fulfill or to do this motion. Then the question is, where did the energy come from to the box to move from A to B? The energy came from you. This act of transferring energy to the box is what we call as work or work done. So you apply the force and the box starts to move, and then it goes from point A to point B. That is work, or we can say work done. All right, now the idea of the work is clear, that work is a method of transfer of energy. This is how you transfer energy to a system. But the question is, if you want to calculate how much energy have you transferred, how will you do that? For that, we have an expression which is work. It can be calculated with the expression force times displacement times cosine theta. This is the expression to calculate work. Here, here F is force under consideration. Then we have D, this is displacement. Then we have theta, which is the angle between force and displacement. That's what work is. Now, since work is a physical quantity which we can calculate, that means it must have some unit. So the units you can figure out just from the expression itself. Um, what are the units for force? Newtons. And what are the units for displacement? Meters. Cosine theta is unitless, so the units for work done is simply Newton meters. But there is another unit which is often preferred, that is joules. Because at the end of the day, what is work? It is a transfer of energy. You are transferring some energy to the system. So this is why work done can also be represented with units of joules. Okay. All right. Now this is the complete expression which we have for work to calculate work done. Um People who are familiar with vectors, students who are familiar with vectors, they will know that this expression is actually the dot product between the two vectors, which is force and displacement. This is the dot product expression. So FD cosine theta actually comes, the cosine theta actually comes from the dot product of A and B. There are two types of products of vectors. One is cross product, which is also known as vector product. This is AB sine theta. Then another one is dot product, which is A dot B. This is AB cosine theta. Now, this is also known as vector product because the resultant is a vector. And this is also known as scalar product because the resultant is a scalar. This is only for the students who are familiar with vectors or who are preparing for JE or APC examination or equivalent examination. For AP1 students who have just um, probably haven't done that much vector for them, this definition, you can ignore the following definition for now. The only definition you need to remember is just force times displacement times cosine theta. That is the complete definition of work done. I know in some schools cosine theta isn't taught. The expression which is often discussed is that force parallel times displacement. That is also a correct expression. It is not wrong. But I feel like that this expression is much more easier to deal with once you start dealing with more complicated questions. Okay, so we are going to work with this equation as we will progress through this unit of work, energy, and power. All right. All right. Since now we know what is work done and how we can calculate work, let's start with some questions. So the very first question we have is a simple one. Let's say we have a box and a force of 100 Newton, is applied on the box moves from A to B. This displacement is 10 meters. The question is asking what is the work done. So you can pause the video and give me your answer. So work done, this is force times displacement times cosine theta. Now force is 100 newtons, displacement is 10. Cosine theta, as mentioned earlier, theta is the angle between the force and displacement. So this is angle between force vector and displacement vector. Both force and displacement are vector quantities. I hope you know that. That is why I am describing theta. And that is why theta is described as the angle between force and displacement vector. So now if you pay attention, force is acting in this direction and displacement is acting in this direction. So what is the angle between force and displacement? It is 0 degrees. They are acting in the same direction. So cosine 0 degrees. So cosine 0 degrees, I hope many of you know that it is 1. So we have 100 times 10. This is 1000 joules. That is the work done by this force. Now, you can calculate work done by any force which is available in the system. It is not just that there are only certain forces with which you can calculate work. Whatever force is present in the system, you can use the following expression and can find out work done due to that force, if there is any. Let's do another question. This time the force is acting at an angle. So this is 100 newtons and the angle at which the force is acting is 30 degrees. The box again goes from point A to B. The displacement is 10 meters. Again, what is the work done? Well, same thing again. Force times displacement times cosine theta. Force is 100, displacement is 10, and cosine theta, if you pay attention, displacement is horizontal in this direction and force is acting in this direction. The theta is already given to you, 30 degrees. So it is cosine 30 degrees. So 100 times tan cosine 30 degrees is root 3 over 2, which can be written as 1.73. So this is 500 times 5 times 1.73. You can simplify this and we get an expression of a value of 866.7 joules. That is going to be the answer. Okay, now notice that from previous example the work done is less, obviously, because the force is acting at an angle. That is why I have this cosine 30 degrees here. If you are familiar with some other expression here, such as this one, work done is equals to F parallel times D. In this case, then what you will need to do, you will then first calculate the parallel component to the displacement and then finally find the work done. Okay, but this expression allows us to simply substitute the value of theta into the expression and then get the answer. Okay, no need to resolve the vectors every time you are dealing with the force which is acting at an angle. All right, let's do another question. Now, this time there is another force present in the system, which is friction. So mass of the box is, let's say, 5 kg. and there is coefficient of friction which is acting, which is present 0 0.4. So the surface is rough. Again, a force of 100 newtons acts on the box. The box goes from A to B. The displacement is again 10 meters. Since there is a coefficient of friction present, that means a frictional force is also acting in the system. Remember that. So let's calculate the work done. Calculate the work done first by applied force. The force you have applied, 100 Newton force. Second, frictional force. Or just we can say friction. Then calculate the total work done. Okay, give this a try and then we can continue with the solution. The first part is applied force. Using the expression work done is equals to 4 Fd cosine theta. Well, force is 100 newtons, displacement is 10. Cosine theta, when we are talking about the applied force, which is 100 newtons, and the displacement, which is 10 meters, they both are acting in the same direction. So theta in this case is 0 degrees. So work done is going to be 1000 joules, something which we have already calculated before. Second is now it is asking to calculate the work done by friction. Now, one thing about friction, I hope you guys remember that it is an opposing force. It always opposes motion. So when the box is moving, we know that the displacement of the box is from A to B, and this displacement is 10 meters. What is the direction of friction when the box is moving from A to B? The direction of friction is backwards. Yeah, because the motion is in this direction. Okay, so this is something which you need to keep in mind. Also, to calculate friction, friction is the formula for friction is mu Fn, where Fn here is the normal force. Now, what is normal force? Normal force is the force. It is a reaction force which appears due to the contact between the box and the surface, and also because there is this weight acting on the box. So the free body diagram which we have is we have weight, which is mg, and then we have normal force Fn, then there is force of friction, and then there is applied force. Okay, so now we need to calculate the force of friction. Here we know formula is mu Fn, and from the diagram we can see that Fn is equals to mg, so force of friction is mu mg. Mu is 0 0.4, 0.4, and mg mass is 5, and g is, for simplicity we are going to take g as 10 meters per second square. Well, I guess I can substitute all the values later on, so I guess we can just simply keep it as mu mg. So work done, this is force under consideration. Remember, when I wrote down the expression, I said force under consideration. So it can be applied force, it can be force of friction, it can be other forces which we will be talking about later in the video. So this is force of friction. So maybe I can write it like this, then Fd cosine theta. force of friction, the value which we have is mu mg. Obviously, if you want, you can like substitute all the values here. Mass is 5 and g is 10, and then calculate the force of friction and then substitute the value here. I just simply like to substitute the value at the end once I have the final expression written down. Displacement is d, and then cosine theta. Now the question is, what is cosine theta here? Understand that as here, what I described here, that motion is in this direction. So the displacement of the particle is in this direction, d. Whereas the friction, force of friction, is acting in this direction. So these are two vectors now which are acting opposite to each other. What is this angle between them? This is 180 degrees. So theta is 180 degrees here. So here, when you will be writing down the angle, this will be cosine 180 degrees. Now we can substitute the values. 0.4, mass is 5, g is 10, displacement is also 10, cosine 180 degree is -1. So work done comes out to be 4 5s are 20, so this is 2 times 10, that is 20, and then 200 and -1, so this will come out to be -200 joules. So the work done is -200 joules. Remember that. So what we noticed that work done, when we calculated the work done by applied force, it came out to be a positive number, whereas when we calculated the work done by friction, it came out to be a negative number. Something which you need to remember. We will be coming back to it. Now let's do another problem. Let's say we have a similar system like before, but this time the force is acting at an angle 100 Newton, and there is friction present, and this is displacement 10 meters, and the angle is, let's say, 60 degrees. So question is, calculate the work done. In fact, let's make it several parts. Calculate first, calculate work done by applied force. Then calculate the normal force. Then next part is calculate work done by the normal force. Then fourth part is calculate work done by friction. And then finally the total work done. By the way, I think I forgot to calculate the total work done in the last example. Let's drag this down here. Yeah, the total work done. So the total work done here, it is going to be just simply work done by the applied force. We can write it as WA, and then work done by the frictional force, which we can write it as WB. So total work done is going to be work done by applied force, work done by force of friction. This is 1000 joules minus 200 joules, and this is going to be 800 joules. That is your answer. Now let's do this problem. Give it a try on your own, and then we can continue with the solution. Okay, so the first part is work done by the applied force. Straightforward application of the formula. This is FD cosine theta. Now all of us are aware what is going to happen here. This is just 1000. This is force is 100. Displacement is 10, and cosine is already given to us, 60 degrees. So that is just half here. This is just half. So this comes out to be 500 joules. This is the work done by applied force. Second, the question is asking the normal force. Calculate the normal force. So first we need to determine what is the normal force. Now in this case, determine the normal force. If you got your answer for the normal force as equal to the mass of the box, then that is incorrect. By the way, mass of the box here is 10 kg. I seem to have forgotten to mention that. Mass of the box is 10 kg here. So determine the normal force. Now, as I was saying, for students who calculated the answer, or who said that normal force is equals to just mg, that is not correct. The reason is because, okay, mg is acting downwards. The normal force appears because of this interaction here. But if and only if there is no other force acting vertically or at an angle like this on the object. Now, since there is a force acting on the object at an angle, that means we can split it into components. So when you will split it into components, this is going to be 100 cosine 60 degrees, whereas this component is going to be this component of the force is going to be 100 sine 60 degrees. So just saying that Fn is equals to mg is not correct, because the system is at rest. That means mg is now balancing both Fn and the vertical component here, 100 sine 60 degrees. Okay, this is the correct expression. I will explain it one more time. If the box was just resting on the table, then obviously in that case mg is equals to Fn, so the normal force would have been equal to mg. But in this case, there is an additional force which is acting at an angle. Now this force, since it is acting at an angle, it can be split into two components, one horizontal component and another one is vertical component. Now if you look at the vertical component, since the system is at rest, it is not being lifted upwards. That implies that both mg and Fn 100 sine 60 degrees, all these forces are balancing each other. Since mg is acting downwards and Fn plus 100 sine 60 degrees is acting upwards, that implies they are equal to each other. So the Fn is equals to mg minus 100 sine 60 degrees. That is the correct value of mg this time. Now mass is already given. I said it is 10, g is 10, 100, and then sine 60 degree. Sine 60 degree is root 3 over 2. We can substitute the value here. So 100 minus this is 100 times, this is going to be, well, 50. Root 3 is 1.73. So the value you will get will probably come around 100 minus 86.5. This will be plus 13.5 newtons. This is the normal force. Okay, so that is the answer for the second part. Now third part is asking us to calculate the work done by the normal force. So work done by normal force. We can start with the expression. This is Ft cosine theta. The force which we are considering is normal force. D cosine theta. Now the question is, before we put in any value, what do you think? What is the theta between the normal force and the displacement here? Pause the video, think about it. Now, if you remember, displacement is horizontal, it is going from A to B. So the direction of displacement is this. Whereas the normal force from the free body diagram, it is upwards. So the angle between the normal force and the displacement is 90 degree. And what is cos 90 degree? That is 0. So it doesn't matter what value of normal force or displacement you have. Since the normal force and displacement are 0, the work done is going to be 0. 0 joules. That's the answer. Next part of the question is, it is asking us to calculate the work done by friction. Again, here things have changed compared to the previous problem because the normal force is different. The normal force is no longer equal to mg. We will need the new value of the normal force which we have calculated here. So work done by friction, this is going to be, first we need to calculate the force of friction, which is mu Fn. Now mu is 0.4, Fn we have already calculated, this is 13.5. So this is 0.4 times 13.5. That is force of friction. And work done, this is force D, and then this is cosine theta. So 0.4 times 13.5, displacement is 10, and cosine theta is, theta here is, well, the theta remains the same because displacement, it is acting in this direction, whereas friction is acting in this direction. So displacement and friction have an angle of 180 degree between them. So this is cosine 180 degrees. You can simplify this cosine 180 degrees as mentioned before. This is -1. So it will come out to be, this will come out to be minus 54 joules. Negative because there is cos 180 degrees there. That's why negative. All right. Now the next part of the question, it is asking us to calculate the total work done. So let's calculate the total work done now. This is, so part part 5. So total work done, this is work done by the applied force, work done by the normal force, and work done by the force of friction. Now work done by the applied force, we calculated that to be 500 joules. Work done by the normal force, that was 0 joules, and work done by the force of friction came out to be minus 54 joules. So the answer comes out to be 446 joules. That is your total work done. Okay. Since this is a video, so if you have any questions, doubts, you can leave your questions and doubts in the comment section, and I will try to get back to you as soon as possible. Also, if you have some problems which you would like to discuss or want me to go over, you can again mention that problem in the comment section, and I will try to include it in the next videos or upcoming videos. One thing we noticed here is that work, sometimes it is a positive value, sometimes it is a negative value, and sometimes it is 0. So the question arises, what type of quantity is work? Is work a scalar quantity or a vector quantity? I mean, if you remember the formula, this is force, displacement, cosine theta. This is a vector quantity. This is a vector quantity. And we just saw that work can be positive, it can be negative, and it can be zero. So what type of quantity is work? What do you think? Well, work is a scalar quantity. When I was mentioning the cross product and dot product, I did mention that work can be written as dot product of two vectors, and dot product is also known as scalar product. That is just for people who are familiar with vectors. Uh, Energy. Work is energy. Energy has no particular direction. So that is why work is a scalar quantity. Okay, because energy has no particular direction of flow. Now, the question arises, what is positive, negative, and zero? Then, how can work be positive, negative, and zero if it doesn't have any direction? Well, what does positive work mean here? Positive work implies that the energy is added to the system. Energy is added to the system. This can also be sometimes described as work is done on the system. This is very similar to the example which we started with, that there was a box and then you push the box in this direction. So what happens? The box moves from point A to B. What you did, you added energy to the system. That's why in this case, when you will calculate the work, this is positive work. Okay. So that's why work can be positive. Now the question is negative work. If you remember the solutions and the problems which we just did, we calculated negative value for work done whenever we were calculating the work by friction. What is friction? Friction is an opposing force. So negative work simply means energy is taken from the system. From the system. Now can also be written as work is done by the system. Okay, let's consider the same example as this one. You push the box goes from A to B, but we know after a while the box is going to stop. Why the box is stopping? There is nothing which is, I mean, visually there is nothing which is trying to stop the box. Then how does, whenever you push something, it eventually comes to a stop? The reason is friction. Okay, because friction is acting on the system, and now when friction acts on the system, it causes a loss of energy. So this is something you can experience, like for example, if you take your hands and then you start rubbing them together, you will eventually feel that they start to warm up. Yeah, due to friction, the hands, you feel heat between your palms. Okay, so similar is the case when the box starts to slide on a rough surface. Friction acts and it causes a loss of heat. So whatever energy you transferred to the box, which was, let's say, 100 joules. I'm assuming a number here. So the 100 joules is eventually lost in the form of heat. That's why the box stops. So it stops because the energy is lost in the form of heat. It has changed into what we will learn about as into thermal energy. Okay, So that is what we mean by negative work, that energy is taken from the system. Now, work done can be zero. What does this mean? Well, to understand this, let's consider a very simple example. Suppose you are carrying a stack of books and you are moving from point A to point B. Let's say the mass of the stack of books is 2 kg. Question is, what is the work done in this case by you? Think about it. Well, if you look at it, you are moving from A to B. This is your displacement. Let's say 10 meters. But the force which you are applying to keep the stack of books steady on your hand, that is upward. This is your force applied. So the displacement is acting in this direction, whereas the force applied is in this direction because you are holding the book in your hands. So to balance the books, you have to apply force upward to keep it steady so that it doesn't fall down to counteract the gravity. Yeah. So the applied force is in upward direction. So theta is 90-degree here. So in this case, the work done, if you notice that, let's say you are applying maybe, since mass is 2 kg, so the force applied is going to be 20 newtons and displacement is 10. So this is 20, 10, but the theta is 90-degree. So work done is 0. That is one case where work done can be 0. Second possible case where work done can be 0 is that suppose there is this multi-story building and you are applying a force to move this multi-story building. Now, obviously, no matter how hard you try, the building is not going to budge. Unless, of course, you have some hidden superpower, which you haven't revealed to the world. So then in that case, FD cosine theta, let's say you're applying 1000 Newton force. Since displacement is 0, doesn't matter what cosine theta is at this point, displacement is 0. So work done is again 0. And final example of work done 0 is when there is no force acting on the object and the object is just simply chilling on the table. Force applied is 0 newtons. No external force, nothing is happening. Object is just at rest. So that will also give me work done 0. All right. So these are the cases where we can have positive, negative, and 0 work done. And even though work is positive, negative, and 0, it is not a vector quantity, it is a scalar quantity. So keep that in mind. Now we can stop the video here. We will do some questions. The next video when I will upload, we will do some additional questions on work, and the topic of work will be finished, and then we will start with the topic of energy. So the theory related to work is just this, what we have discussed so far in this video. In fact, what I'm going to do now, I'm going to put two questions as for you guys to try, and then in the next video I will go over those questions. Okay. All right, so the first question we have is, it says a snowboarder reaches the bottom of a hill and then glides to a stop in 16.4 meters along a horizontal surface. The total mass is given to us. The total mass of the skier and the board is 64.2 kg, and the coefficient of kinetic friction is given. Coefficient of kinetic friction mu k, that is given as 0.106. So this is between snow and the board. So what you need to determine for this problem is determine the magnitude of kinetic friction, and the second part is work done by friction. That's what you need to determine. Second question as practice for you guys is one thing. Well, if I don't find the question, then I guess this is it for this video here. What we have done in today's video, we have talked about, we have started our discussion on work, and we understood what work is. We also learned about how to calculate work done for different types of forces. Then we finally learned that okay, work can be positive, negative, and zero, but it is still not a vector quantity, it is a scalar quantity. So, and we did quite a few questions on the topic as well. Now, in the next video, we are going to do some more questions on work, and then we will start talking about energy. I hope the video was interesting for you. Obviously, you can drop your questions in the comment section, and you can also drop some suggestions regarding to how to improve the video. All suggestions are welcome. So this is it for this video, and we will see each other again in the next one. Take care. Bye.